Welcome. You have arrived at the Swagelok Tech Talk, how to right size a pressure regulator for flow and pressure. So your presenter today is Brian Jalbert. He is one of our wonderful field engineers with Swagelok and very well versed in regulators. And he's going to take you through some good topics today. So we'll go for about 30 minutes here and then answer questions at the end of the presentation and stay on as long as we need to address those questions. So feel free to type those in at any point and we will get through to everyone as we can. So go ahead and take it away, Brian.
Sounds good. Good morning, everyone. As she mentioned, my name is Brian Jalbert. I'm a field engineer over at Swagelok Cambridge out in New England. And today we're going to go over some of the other topics that weren't covered in the Tech Talk, first Tech Talk. And then we're going to go over some common applications where regulators are sized incorrectly because we're not given enough information. And then we're going to start showing you guys how why we don't like to size regulators using the CV rate. And I'm going to go through a few examples that really demonstrate why that doesn't work out. And then I'm going to show you how to use the flow curves to their fullest capabilities and how to interpolate some of the curves. And then we're going to go through a few examples of that because it's really the most difficult and most commonly, misperformed activity. And lastly, I'm going to go through another tool that we call the flow curve generator, and it's generally used for higher flow regulators and process regulators. And we're going to talk about some downstream velocity and how that can also affect the limitations of a regulator's performance. So the first topic we're going to talk about today is critical flow versus subcritical flow. And ideally, we want to have critical flow through a regulator, even though it sounds scary. Really what that occurs is when your inlet pressure is at least double your set pressure. So ideally, if you want to have 50 PSI going through a regulator, you want to have at least 100 PSI or greater as the inlet pressure. When you're running at subcritical flow, there's a correction factor that has to be applied if you're actually doing calculations without flow curves, because it creates a lot more droop when it doesn't have enough pressure differential to push the flow through that regulator. And the flow curves are already compensated, so you don't need to apply a correction factor. But if you remember the flow curve we see here below, we've got our flow axis on the x-axis and our pressure on the y-axis. And I've got a subcritical flow scenario shown here where the inlet pressure is 100 PSI, and we're setting that regulator to 100 PSI. And as you can see, with a subcritical flow, the droop is very dramatic. Just increasing that regulator inlet pressure to 500 PSI really increases the accuracy and allows you to get pretty much up to 10 CFM out of the same regulator that you wouldn't even get maybe 1 or 2 out of with the low differential pressure across the regulator. Excuse me. So the next thing I want to show you guys is some applications that are commonly missized, or if you want to provide us with more information up front, or just let us know that this is going to be used for these types of things, it's going to make a huge difference in how we help you guys select that regulator. The first one is leak testing. In the past Tech Talk, we talked about the minimum information required to size a regulator, i.e. inlet pressure, set pressure, what's going through it, temperature, things of that nature. But there's also some application information that's really helpful. The first one I'm going to go over is the easiest, and that's leak testing, where we're filling a fixed volume to a pressure just to make sure that it holds that pressure. However, a lot of times these requests get sent over where I've got a 10 cubic foot volume and I want to purge that in 1 minute. So they'll say they need 10 CFM at 50 PSI, and we're going to size a regulator that's drastically oversized, where if they told us they were leak testing to 50 PSI, that's going to be much easier because you don't care about droop when you're leak testing. It doesn't matter how much the regulator droops while you're filling that container. What you're really going to be worried about is your lockup pressure and your creep. Now, creep is once that leak test has reached its maximum pressure, you want to make sure that there's no creep across the seat. And you do that by, if you remember the last Tech Talk, making sure there's filters upstream of the regulator and that your regulator seats stay as clean as possible. Another nice thing to remember for leak testing is these regulators are going to be constantly closing. every single time that it fills up to that set pressure, it's going to shut off. So with a leak testing application, you want to look at a regulator with a hard seat. It's going to give it a little bit more longevity, especially if it's leak testing to a high pressure, which is generally what most of us are doing. You're doing a high pressure test to make sure it's going to hold in the environment that it's going into. So peak seats are great. PCTFE seats are also pretty useful for that. Another thing that's commonly done wrong with these is the idea is, oh, I want to do as many tests as possible in a day, so I'm going to pick a regulator with a higher CV or a higher flow rate, just so I can fill that volume as much as possible. However, higher CV rates also have higher lockup pressures and higher supply pressure effect. So as your gas supply drops, you're going to see a change in set pressure, and you're not going to get as accurate of a leak test. Also, your higher valves are going to have more lockup pressure. So right up here, where that spike is when the flow stops and the leak test is actually being performed, it's going to be higher with the larger CV regulator. So when you're leak testing, sometimes it's a great idea just to go a little bit smaller. Excuse me. Now, another odd application where we're not concerned with droop is, we are concerned with droop, but not to the extent that we are with normal flowing applications, is when we're purging equipment. And it jumped to, here we go. So this is commonly done. I see this a lot in vacuum chambers and laboratories, and they need to be able to purge whatever the experiment was out of the vacuum chamber. But they can't exceed, let's say, 50 PSI because it'll damage equipment that's hooked up to the vacuum chamber. However, if they say I need to purge, a 400 liter container, and I've only got 100 PSI inlet pressure to do it, and they say, just like normal, I need to be 50 PSI, we're going to look for a regulator that's going to be able to provide 50 PSI at 300 liters per minute. Where if they had mentioned that they were going to be purging a container and they can't exceed 50 PSI, they don't need to maintain that 50 PSI, we're going to allow them to use a much cheaper and just easier regulator. So what will happen when they are trying to purge is, yes, the droop will cause the pressure to drop down to maybe 20 or 30 PSI. But like we mentioned, we don't care what the pressure is while we're purging. All we care is that there's flow through the test chamber and that it's pushing that contaminated media out of there. So let us know if you're ever doing leak testing or purging. It's going to make a difference to which regulator we select. Those are the two most common applications where accuracy is not important, or not as important, I should say. Purging, sometimes it can be, but every job is a little bit different. This is the most common type of regulator that we're going to talk about. And this is the real reason we love to use flow curves, and I'll get into those in a minute here. Generally, a point of use regulator is something you see on the wall in a laboratory, or it's a secondary regulator at a piece of equipment. Usually it's supplied by a gas source, like a lab bench or something in the basement of a laboratory building. Lockup and creep are kind of a problem, especially if you're hooking up to the thing, but generally these are being supplied by something that already has pressure relief valves, and the first stage regulator is already compensating for supply pressure effect. So really all we need to worry about with this is, can this regulator supply my piece of equipment with enough flow at the pressure that I need it at? And we're going to go through two examples of how to interpolate some curves and really figure out how the flow curves can be used to size these. And the last example I'm going to skim over because we're going to do it at the end of this presentation is bulk regulators and process regulators. These would be bulk supply regulators for an entire building, where there might be multiple labs that have multiple pieces of equipment downstream, and you're going to supply a very large, maybe these are generally going to be ½ inch and above regulators, and there's an excellent tool for sizing those as well. So the first thing we're going to do is explain why we can't size with the CV rate. And I run into this a lot. You can, on the left side of my screen here, you can see there's our Swagelok CV calculator from our website. It's commonly used to size needle valves, ball valves, orifices, things like that. But I'm going to show you a lot of times what happens is someone tries to use it to size a regulator. And so we're going to run through a little example here where we've got a 500 PSI inlet pressure, a 100 PSI set pressure at 70 degrees nitrogen, just to keep things simple. And we're going to use a KHF series regulator, which has a 1.0 CV. So when you plug that into the calculator, you come out with a flow value of 240 plus or minus CFM. However, if you remember the last Tech Talk, when we are sizing a regulator with the CV rate, we are sizing the regulator when it is fully in the fully open position. And when the regulator is in the fully open position, it's operating at choked flow and it's no longer regulating the pressure. So by sizing with the CV, you're essentially sizing the regulator on the flow curve somewhere way out here, way past where the regulator can effectively control that pressure. So depending on the designs of the regulator, it's going to determine how much of that CV rate you can actually use. We used to kind of tell people that use about 30% of what your calculated CV rate is, but I'm going to show a few examples of why you really can't go by that and why we really want to use the flow curves for this. For this example, if we were saying 30%, if you look at this flow curve, under the same conditions that we have under the CV calculator, with a 500 PSI inlet pressure and a 100 PSI set pressure, this regulator really maxes out and the droop becomes pretty substantial, around 40 CFM. So if you size this with the CV, you're going to be 200 CFM short of what you thought you were going to get to this regulator. And that doesn't mean that this regulator is poor performance. And there's a lot of things you can do. They're designed for certain things. For example, this is a 3600 PSI regulator and it's a metal diaphragm. I'm going to show you how certain options of the regulator and accuracy improvers can really allow you to use more of that calculated CV rate. So we're going to look pretty much at the same example here, except we're going to look at an LRSN4 series regulator, which in theory, if you're stuck on that CV mentality, is going to provide less flow and less performance than the KHF because the CV rate is 0.73. However, because of the design of this regulator, it's got a longer spring, elastomeric diaphragms that can travel farther, and just a soft seated design that doesn't have as much lockup. And you're going to be able to see that even though our CV calculated, let's say we took 16% of it like we did before, we should only be able to get 20 to 30 CFM through this regulator. However, with a 500 PSI inlet pressure set to 100, this regulator really performs and really only starts to see substantial droop all the way out to 200 CFM, even though it's got a smaller orifice than the KHF series. And this is also true for other accuracy improvers like dome loading mechanisms for the regulators or external feedback to pilot or external feedback by itself. I don't have time to get into those in this presentation, but really what they do is, depending on your sensing element and how the loading mechanisms are done on these regulators, it allows you to utilize more of that theoretically calculated CV value. For example, we talked earlier how this one's only using about 16% of its theoretically calculated max flow. This regulator can use approximately 90% because of how the design of the diaphragm and the spring is done. So the first question I get whenever I talk about this is, well, then why don't we just only use this regulator? There are some benefits to some of these regulators, even though it is a little less, it doesn't have as flat of a droop curve. It's a stainless steel diaphragm, so the chemical compatibility is unmatched, and a hard seat is going to be a lot more robust and chemically inert than you would get with some of the more accurate regulators. Excuse me. So since we can't size with the CV, we got to find flow curves for all of our regulators, and that's not always available. But I do want to show you a resource from Swagelok that's not in the regulator catalogs, but I highly recommend that you download it because it is a wealth of information. There we go. So the first few pages are really just some technical information about regulators. It's really a summary of our first Tech Talk. It talks about droop, supply pressure effects, lockup, all those things. It also has correction factors for different types of gases and how to calculate those if you've got your own specific gas. It's also got the correction factors for temperature. But other than that, this is a over 200 page document just filled with flow curves for almost every single regulator in our K series catalog and some of the regulators in the process or RHPS series. And I'll just go through and show you just an insane amount of technical data for every single regulator and every single option for that regulator. So let me see here. The next thing we want to look at is now that we've got our flow curves, we've got all this information that we can use. The problem is we really don't have a flow curve for our exact application. The odds that your application is exactly at the set points where they fill out these curves at 15, 25, 50, and 100 PSI is probably slim to none. And they've also graphed different inlet pressures as well. So I'm going to show you guys how you can interpolate these curves and really get them fine-tuned for your exact application. There we go. So we're going to look at a theoretical application where we've got 300 PSI coming in. It's nitrogen. I chose nitrogen because all of our flow curves are generated with nitrogen, and I didn't want to have to go through the chemical, the flow calculations conversion for the different gases, just to keep it simple. We have a system that's constant flow. Remember, I talked earlier about whether that's important or not. And we're also basically what I'm saying is we've only got one piece of equipment that's going to use this regulator. So the flow is not going to be changing over time. It's either going to be 10 CFM or 0 CFM. And we're going to need that at 35 PSI. So to find out if this regulator can do that, the first thing we want to do is find a flow curve that we can use to estimate the performance through this regulator. Unfortunately, we don't have a flow curve for 300 PSI. But we can interpolate this curve. Ooh, there we go. And kind of estimate the curve between the 100 and 500 PSI. Obviously, if it was inlet pressure of 400, it would be a little bit closer. And if it was closer to a 100 PSI inlet pressure, we'd be closer to the 100 line. Now, I only like to interpolate curves when we're running at critical flow, which is the inlet pressure is at least double the set pressure. If I was interpolating a curve between the 150 and we're setting this to 50, obviously we're less than 100 now, I would interpolate this curve very close to the 50 PSI generated curve. Let's say we were trying to do 75. Because we're underneath that subcritical flow mark, you can't just put 75 right in the middle of this. It's going to be closer to the 50 line because of that subcritical flow calculation. So I really only like to interpolate flow curves when we've got critical flow. So that gives me my flow curve. I can now use this flow curve and move it up and down on along the pressure axis to determine what my regulator is going to look like at different pressures. And we need to do it at 35 PSI, and it's going to settle there real quick. And we'll be able to see that this regulator is easily going to be able to provide 10 CFM without a problem at 35 PSI. You'll notice that while I was moving that regulator up and down, that flow curve up and down, I didn't drop below this 25 generated flow curve. Regulators perform a little bit differently at different pressures. That's why we graph the flows at different inlet pressures. Also, another thing to keep in mind is this particular flow curve only has one control range on it. So this is a 0 to 50 control range spring. A lot of flow curves have multiple springs graphed on the same curve. So there might be a 0 to 25 curve on there. And if you use that 0 to 50 PSI extrapolated curve and bring it down below 25 PSI, and there's a 25 PSI curve on there, you're not going to get the same performance. So you want to make sure that if you're in between here and here, and you can only move this down. Also, I like to move flow curves down, not up. So I would never extrapolate a flow curve here and then move it up to 50 PSI, because you can end up in a subcritical flow situation. And as your inlet pressures increase, you know what's going to perform better when the regulator flow curve is moving down instead of up. If you do need to interpolate a curve below this, just run another curve between this 500 and this 100 curve and use that curve below this 25 PSI set pressure range. So another example, this was a constant flow example. I'm going to run through one more that's a little more complex. And it's also another great request for more information. We talked during the earlier part of this presentation where we're always just given the bare minimum information. Set inlet pressure, set pressure, maximum flow rate, and maximum flow rate doesn't really help us. Ideally, if we've got a variable flow, we need to know what that is. And it's also extremely helpful to know what the tolerance of your set pressure is. So most of the time people are saying, oh, I need this at 30 PSI for this example. But is it plus or minus 1 PSI, or does your equipment fail anywhere? A lot of times that's not known, but it's extremely helpful when it is. And we're going to run through a quick little experiment here where we're going to figure out which regulator to use for a 30 PSI system with 250 PSI inlet. And in this time, instead of a constant flow, we're going to have two pieces of equipment that can be on or off. So our flow rate can either be 2 or 4 CFM. And we're also going to go and size this regulator, assuming that there might be more units added in the future. So we're going to look at a couple different curves. I'm going to pretend like we jumped over to that technical bulletin that I showed you a moment ago. And we're going to look at a few different curves, just trying to find one that has somewhere between 2 and 4 CFM and our 30 PSI set pressure. So the first one I'm going to look at is just the KLF. And we'd have to extrapolate a curve to approximately here. And it's looking like it's going to be kind of steep between the 2 and 4. It might make the application. It'll probably be enough for just these two. But I'm betting if we extrapolate it down, it's not going to work. So I'm going to jump to the KHF and do exactly what we did before. We're going to find a flow curve, interpolate it between 100 and 500 because we have a 250 PSI inlet pressure. Then we're going to graph our set pressure and our tolerance. And then we're also going to graph our flow ranges. So we've got our first piece of equipment at 2 CFM, our second at 4, and the future equipment at 6 CFM. Then we can move our flow curve down approximately the center, and we can see that when one piece of equipment is running, we're going to be at about 31, 32. When both of them are on, we'll be right at 30 where we want it. And you can really predict that we could potentially add up to 5, maybe even 6 more 6 pieces of equipment to this same regulator before its droop curve is going to exceed our tolerance range. We can also see that when only one piece of equipment is running, we're not running in the lockup range of the regulator. Don't want to really operate a regulator in this range. It's a little unpredictable. You can see that the pressure droop is pretty steep, and this is really the best part of a flow curve to use, and the best performance you're going to get out of any regulator. So those are the best tools we can get with the most analytical lines, which is generally our 1/8 inch through 1/2 inch K-series regulators. I highly recommend using these curves and using these methods to figure out if your regulator is going to be able to provide enough flow over the range of, provide this pressure that you need over the range of flows for your applications. So the next thing we're going to take a look at is calculating larger sized regulators. And when you start getting into larger process lines, one of the common limitations is actually the downstream velocity of the regulator. So we're concerned about the velocity on the outlet side of the regulator that could be the limitation. And that's not to say that the smaller regulators in the K-series don't have a velocity limitation as well. Every flow curve that we just looked at in the technical bulletin is demonstrating flow through the seat of the regulator. So it's only calculating the flow through this orifice. So if you're looking at a flow curve for a 1/2 inch regulator and you think, oh, I can easily get this much flow through it, but then you drop a 1/4 inch adapter on the outlet of that regulator, the velocity is going to increase so much that you're just not going to be able to provide that kind of flow. It's basically just a flow restriction. So keep in mind that just because the flow curve shows you that you're going to get that much flow, you absolutely need to make sure that your line size downstream of the regulator is at least the size that's at the very beginning. Like, don't drop a 3/4 inch regulator down to 1/4 inch tubing. You will not be able to get that same performance curve. And I'm not going to get into the gas velocity calculations because they take a lot of time, but I am going to show you the flow curve generator, which has a velocity calculation built into it. So this is an excellent tool for sizing the RHPS regulators or the larger regulators of our line. They are available in 1/4 inch as well, but this tool is primarily for the 1/2 inch and above process systems. And it's a pretty straightforward tool on Swagelok.com. You're also able to compare multiple regulators at the same time. So if you want to compare applications, and I'll show you guys how we can set this up. You do need to have the catalog open next to it, and I'll explain why in just a moment. So you can also change your units. We're going to stick with the defaults, but if you prefer to work with bar, MPa, whatever you want, and your flow units, everything can be changed to whatever territory you happen to be working in. So I took the liberty, in the interest of time, of pre-filling out this with an RS4 regulator. And that is a 1/2 inch spring-loaded regulator, pretty basic. Excuse me. And I used a pressure control range of 2, which gives us a 0 to 100 control range. And our inlet pressure is 500, and our set pressure is 100. And this is going to generate a flow curve for this regulator. However, it's also going to generate a velocity curve. Excuse me. And as we can see, the velocity on this regulator is kind of limiting our flow to about 30 CFM. So this is going to be our flow curve for the flow through the seat, but anything over 30 CFM is going to start having, it's going to reach sonic velocities. You're going to have extreme noise and potential vibration. It can cause all kinds of problems downstream for other components and for the regulator. So when you are sizing larger regulators, this velocity curve does come a lot into play. And I'm going to show you another example of how you can play around with these. Just by selecting the regulator. So I'll drop an RS6 regulator into here, for example. That is a 3/4 regulator. The tool automatically changes the outlet tubing to match the worst case scenario for that regulator. So in the case of an RS6, that is a 3/4 regulator. This is the approximate ID of 3/4 schedule 120 piping. So if you're using 3/4, excuse me, 3/4, let's say 065 wall tubing, so it's going to be approximately 0.625. You can actually adjust the outlet ID, and that will give you a little bit less velocity downstream. And I'm going to demonstrate on the next curve. The other thing that this tool automatically does is does all of the different gas correction factors for you. So if we wanted to run methane through this system instead of nitrogen, it would automatically put in the recommended line velocity, which is that velocity I was talking about downstream of the regulator. Methane flows fairly fast, especially gases like hydrogen and helium. The velocities are very, very high. So if we did the same calculation for hydrogen, it resets your control range here. There we go. If we do that same calculation for hydrogen, you can see that our velocity curve allows us much more flow because hydrogen is a much smaller molecule and the volumetric flow rate is so much higher. And then the other example could be for oxygen, where we want to have oxygen flow at much lower velocities. It's a pretty dangerous gas because of particle impaction and the potential for fires. You're going to see that that velocity curve automatically drops down, and that's just to make sure that the system is safe for that application. So I'm going to show you guys another example of how that velocity affects the flow rates. And I'm comparing 3 regulators here, which is from my first example. This is an RS4, 6, and 8. And as you can see, all 3 of these regulators pretty much provide the same flow rate through the seat of the regulator. So they got a very similar flow curve. However, the RS4 with its 1/2 inch MPTN connections is limited to approximately 30 CFM, where the 3/4 inch end connections are going to allow you to go out to about 60. And the 1 inch regulator is going to allow you to pretty much utilize that entire flow curve that's available. It's just a really excellent tool for finding those types of situations. Another thing I love to use for this tool for is to compare other kinds of regulators. For example, let's go look at so I want to find a regulator that's kind of good for a process application. I'm going to scroll down to, let's say, an we're going to find a 1-inch regulator here. So the RD8, and I'm going to find this regulator and say that I kind of like these pressures, but I can't quite tell how it's going to look in my exact application. So you can go into the flow curve generator, put that first regulator in, and you can actually put your application right in. In that example, this would be that first regulator that I picked. That's an RS8. It's a 1-inch regulator. However, looking at it, the flow's pretty steep. It might not be able to be as accurate as I need. That doesn't mean you need to go to a larger regulator. And this is the emphasis I always put on anything with a regulator. And the mentality that's always given by CV calculating flow with a CV rate is I need to go larger. With regulators, you need to go more accurate. All 3 regulators that I have graphed here have the same CV. So this is an RS8 regulator. The same exact regulator, I talked earlier about adding accuracy options like dome loading or dome loading with external feedback. This is that same regulator with the spring replaced with a dome load. And as you can see, it just dramatically increases the accuracy and allows you to utilize that regulator. And I love using this tool for comparing that and sizing major gas distribution systems, because you can compare all 3. And if you need more accuracy, you just tag on one of the options with external feedback. And you can actually see, you can't even see the graph for the external feedback option because it looks like a flat line. External feedback to pilot makes regulators extremely accurate and really allows them to utilize pretty much the entire theoretically calculated CV rate that we talked about before. So those are the 2 most common ways that I like to size regulators. The biggest one is the flow curves, most common. And when you get into the larger flow systems, that flow curve generator is an excellent tool. And I'm going to ask you guys whatever questions you have in a minute. But I did want to mention that we are going to have another tech talk in the future, possibly on maintenance and troubleshooting. We'll let you guys know what it's going to come up with. And are there any questions?
Okay. Yeah, it looks like we have a few questions. Let's see. Let's start with Chris says he's a mechanical engineering student at UCSB. He's working on creating a pressurized air system for a fluidized bed reactor for a project. In order to create fluidization in our material, we need a minimum flow rate of 12.5 inches /S, sorry, and a minimum pressure of 56 PSI. The plumbing system will include pneumatic pipes connecting from a pressure vessel to a pressure regulator, then connecting to a flow meter, solenoid valve to the gas distributor plate. Is there any advice you can give on choosing the correct pressure vessel and compatible pressure regulator that would be able to sustain these pressure and flow rates to run an experiment for 3 minutes? So they're working with compressed air. So do you want me to send that?
Yeah, let's do that one in an email just because it's going to get a little complex.
Yeah, okay.
And we need to estimate what your flow rates would be as well. Flow is such an important thing when trying to size a regulator. Let's look up what the requirements are of that solenoid valve and whatever else is using it downstream.
Okay. So there were a few other questions that were submitted prior to the webinar, but I think with those as well, we want to address those on an individual basis. Anyone else have anything kind of after hearing the presentation today that we could help you with further here? Maybe not specific to an application currently, or kind of high level stuff you're encountering. Okay, so here's one. So thinking about the variable flow case, if you had one reactor running at turn down, it would put you in the lockup range. What would you do for that case? You said you mentioned a dome loaded regulator earlier. Would a dome loaded regulator have better or worse lockup than a spring loaded?
Well, it'll have more lockup ultimately, but it might reduce like where the area is. A dome loaded regulator might have that. You might be better off with a higher sensitivity regulator, so a larger diaphragm regulator, or actually if you don't have that much flow, go with a lower CV regulator. So the lower your flow, the further you are from this lockup range. And, or let's actually, I'll show you a perfect example right here on the flow curves. Control home. And of course, my control buttons don't work in Zoom. So there we go. All right, so we're going to look at, let's say this is just a 1/4 inch regulator, but it's available with 4 different sized orifices. So if we look at, let's say we're looking at a 0.2 CV, oh, I went by it. A 0.2 CV at approximately 25 PSI, we can see the lockup range kind of ends at about 0.5 CV, I mean 0.5 CFM. So if we go look at a smaller CV range, which is a 0.06, 0 to 25 range, we can see that the lockup range really doesn't start until about 0.1 CFM. So by going with a smaller CV regulator, you can ultimately move that lockup range a little bit further over to the left. Now, if you still need the full flow control range all the way out to the 8 CFM, then you might want to look into a regulator like maybe a dome loaded regulator, but we'd have to size a little bit and experiment with the flow curves to see how accurate we can get it. And then there's also another type of regulator I'll show you, which is a version. So this is your standard spring-loaded regulator. These, as long as it's low pressure, you can use what we call an LPRS regulator. And it's essentially a very large diaphragm regulator like this. So it's very similar to the one you saw earlier, except it has a very large sensing element. And that dramatically reduces lockup and supply pressure effect. And it's extremely accurate as well. You can kind of see the flow curves actually go in a reverse direction. And that's because of a suction tube, which I don't have time to cover here, but it really allows those regulators to be very, very accurate over the entire flow control range, provided you don't need more than 50 PSI.
What about a metal seat versus soft seat?
Really depends on your chemical compatibility is the most common reason. Soft seats are generally used for softer applications. I mean, lower pressure applications where a hard seat would be a high pressure or a chemically inert application. So some of the benefits of a soft seat are they do have lower lockup, and they do a little bit better at preventing creep because the O-ring seals can kind of mold around any particles that might hit, where a hard seat like a PTFE or a hard plastic, if there's any particles in there at all, it's going to kind of hold the poppet open and you're going to get creep. So, but again, that soft seat's going to be torn to shreds the moment you get high pressure. So it's kind of dependent on your pressure. Once you get in any high pressure situation at all, you're going to have to go with the hard seated regulator. That's just the formula of it.
Okay. Thank you so much. Any other questions? It's like we got the big ones came in early, so we will follow up directly with whoever submitted those. There were a couple, like I said. So I think based on that, we will make sure that you have access to the recording. You can actually use the link that you joined the Tech Talk with this morning to review the recording after it's complete here. And then if you do have any other questions, feel free to defer those to your sales and service center, and we will make sure to bring Brian in as needed for expertise or some of the other field engineers in the area. So with that, I think we will go ahead and let everyone go for the day here. Thank you so much for your time, Brian.
No problem. Thank you.